Suppose let's say sigma is a map from R to S, both are rings. Okay, is a ring homomorphism. Is a ring homomorphism. Now consider the map. Consider the map sigma tilde from Rx to Sx such that what does it do? So it takes a polynomial, let's say a0 plus a1x and so on till an x to the power n. So this is the polynomial coming from Rx, and it maps it to sigma of a0 plus sigma of a1 times x and so on and so forth till sigma of an times x to the power n. And clearly this is in Sx, right, as each sigma ai is in S, since each ai is in R. Is it clear? Is it clear? Right. Now also that it can be pretty easily observed that this function sigma tilde is well defined. It's some sort of an extension. You can see that sigma tilde, if you restrict it to R, then this is exactly sigma, nothing else, right? If you have studied analysis, then you can see that this is some sort of an extension. Moreover, the other thing which is important, that you can just write it on your own, that from the homomorphic nature, clearly observable from the homomorphic nature of sigma, sigma tilde is also a ring map, is also a ring homomorphism, right? Okay, so now let's make use of this tool a bit. Okay, fine. So theorem, let's analyze the importance of this very tool which we introduced. Let R be an integral domain. Let R be an integral domain. Let F be a field. Okay, let sigma be a map from R to F, be a ring homomorphism, and let Px be an element be in Rx. Fine. Now if the degree of P is same as the degree of sigma tilde of P, right? Sigma tilde is the map we defined here. Okay, it is the extension of sigma to the ring of polynomials over R and F. Okay, right. So what we are claiming is that if the degree of the polynomial P is same as the degree of the image of P under the extended map sigma tilde, and if sigma tilde of P is irreducible in Fx, then Px is not a product of two polynomials in Rx, each of degree less than the degree of P. Is it clear? Okay, fine. Let's study the proof once more and then we will let's study the theorem once more and then we will prove it. So we are given R to be an integral domain, F to be a field, sigma be a ring homomorphism from R to F, right? Then what we are claiming, that if the degree of P is same as the degree of sigma tilde of P, and if sigma tilde of P is irreducible in Fx, then Px is not a product of two polynomials in Rx of lower degree than P. Okay, proof. Okay, first thing, this is sort of a remark. You can easily observe it as a remark that the degree condition as in this condition, that is the degree of P is same as the degree of sigma tilde of P, can be avoided, or rather is immediately true if P is a monic polynomial, right? If P is a monic polynomial means the leading coefficient is 1, because then what would be the leading coefficient of sigma tilde of P? It should be sigma of 1, that's 1, we know from the properties of ring homomorphism, right? So the degree must be same, right? Fine. So if I start with a monic polynomial, then I do not have to explicitly mention this condition, but rather nevertheless let's talk about the proof of the theorem now. Okay, fine. Suppose I can write Px as f of x times g of x in Rx such that the degree of f is less than P and the degree of g is also less than P. Okay, we want to show that there exists a contradiction. This is my symbol for contradiction. We want to show this. Okay, now observe that in fx what happens. In fx it is pretty obvious that sigma tilde of p will be sigma tilde of f times sigma tilde of g, right? Because sigma tilde is a ring homomorphism. That is pretty clear to observe, right? Now sigma tilde of p is given to be irreducible, right? What does that mean? That means that sigma tilde of f or sigma tilde of g is unit, right? Is it clear? Okay. So what can we conclude from here? That so without loss of generality, let sigma tilde of f be a unit, right? Now sigma tilde of f is a polynomial in fx. We know the only units in fx should be the units coming from f. So in other words, it's a constant polynomial, right? So its degree must be 0, which implies that the degree of sigma tilde of f is 0, right? But then what happens? Then now clearly observe, now the degree of p is given to be same as the degree of sigma tilde of p, but the degree of sigma tilde of p is the degree of sigma tilde of f times the sigma tilde of g, right? But both of these are coming from polynomials over fields, right? Both of these are coming from polynomials over fields. So polynomial over fields are integral domains. That is an integral domain. So we know that over integral domains, if I have a product of two polynomials, then the degree of the product must be sum of the degrees of each polynomial. So it must be the degree of sigma tilde of f plus the degree of sigma tilde of g, right? Is it clear? But then we already have this in hand, the sigma tilde of g is 0. Degree of the sigma tilde of g is 0. So this is equal to degree of sigma tilde of g. Now it is also sort of clear that this is again sort of a remark which you can establish pretty obviously, that uh, you know, if I talk about the degree of g, then this is rather if I talk about the degree of sigma tilde of g, then this is at most the degree of g, right? Why is it so? Because the map say sigma of an can be 0, right? Sigma of an can be 0. Sigma can be such a ring homomorphism that sigma of an comes out to be 0, right? In that case the degree will decrease. If sigma of an is not equal to 0, then the degree remains the same, and if sigma of an is 0, then the degree decreases. So the degree of the image of g under sigma tilde must be at most the degree of g, right? So what do we conclude from here? Therefore this must be less than or equals to degree of degree of g, right? But the degree of g was assumed to be less than the degree of p, so it's a contradiction, right? Hence we complete the proof. Is it clear? Is it clear? Let us talk about an example, immediate example. Okay, let f of x be 8x cube minus 6x minus 1 in zx. Fine. Okay, let me add one more remark. This is a slightly more important sort of a remark, that suppose R is given to be a domain, right? R is an integral domain. We know that I can consider f of R, right, which is the fraction field of R. So it will work in these pairs, right? I can start with an integral domain and then I can talk about the map from R to its fraction field. Okay, make it very clear, because in most cases we are going to talk about polynomials coming from Z, and again we'll always talk about the correspondence of elements coming from Z to elements coming from its fraction field, which is just Q. Fine. And our main focus is to talk about polynomials from Z or from Q, right? So let us choose a polynomial f 8x cube minus zx, right? And let me do one thing. Let yeah, so I don't think we will require q in this case. We'll require q later, but I added the remark thinking that I would require q here. Let us choose a map sigma from z to z5. Okay, so the sigma takes n and it takes it to its equivalence class in 5, that is n mod 5. Fine. Okay, then what is sigma tilde of f of x? So it should be 3x cube, right, minus x minus 1, right? And observe that this you can take as an exercise, or you can try and prove it, that this is irreducible in z5, or rather z5x. One way of checking the irreducibility, what you can do is that first try and check whether it has some root or not. and the check is very easy whether it has some root or not, because these are 3-degree polynomial. Recall 2 and 3-degree polynomials, to check existence of root, directly choose values from the set and put, and see whether it evaluates to 0 or not. It won't work for higher degree polynomials. Fine. So I think this is clear, right? So posteriorly, that once it is irreducible, check is an exercise to check whether it's irreducible or not in Z5x. What do we conclude is that, so this implies that I cannot write f of x from the previous theorem, because one more thing to observe here is that the degree of f is same as the degree of sigma tilde of f. Right? Z is a domain, Z5 is a field, because Zp is a field if and only if P is a prime. So this implies that f of x cannot be written as a product of polynomials in Z of degree less than 3. Clear? Fine. Okay. Now what our aim is to do, so this you can think of some in some sense a proof of trying to write a polynomial as a product of two polynomials of lesser degree, which exhibits some sort of a factorization over integral domains. So this is some tool concerned with factorization over integral domains, or what we call a proper factorization. This is something called a proper factorization over domains or integral domains. Fine. But we need some stronger tools. Okay, we need some stronger tools for evaluating polynomials over fields. Okay, and towards that we are going to move now. Okay, fine. Definition. To start with the definition. So a polynomial f of x equal to a naught plus a1x till a n x to the power n in Z, I mean over Z, is called primitive if the GCD of its coefficients is okay. Fine. Right. A more general definition of a primitive is fx in polynomials over rings is said to be a primitive if the GCD of the coefficients is a unit. Right. So R, for example, let's say R is a UFD, because at least I want to talk about the existence of a GCD, right? So let R be a UFD. Okay. So a more general definition is talking about units, but since we are concerned about polynomials over Z, so the GCD is defined to be just 1. I mean the primitive is defined for to polynomials whose GCD is 1. Now observe the following. Choose this polynomial, let's say 3x square plus 6x plus 9. Okay. Fine. Choose this polynomial in Zx. So what is the GCD of its coefficients? It's 3, right? So GCD of 3, 6 and 9 is 3. But then what if I divide it by 3? So let this polynomial be f of x. So then what is 1 by 3 f of x? So 1 by 3 f of x is x square plus 2x plus 3, and then clearly this is a primitive polynomial. Right? And you are sure about the fact that the leading coefficient is 1. Right? One more observation which you can immediately get from here, that primitive, monic polynomials are always primitive, right? Monic polynomials are always primitive. That is why in most books on ring theory you will see that more analysis is done on monic polynomials, because that's already primitive, and most of the cases we require to check about irreducibility, so on and so forth, requires the notion of the polynomials being primitive. Nevertheless, fine. Okay, so this is the case what we have in hand. So what do we observe it in a more general sense is that if D is the GCD of the coefficients of fx, let's say in Zx, or rather this also holds true for polynomials in general, but since we are talking about an effective division, okay, so rationals and integers are the one we are concerned with typically in this case, then 1 over D multiplied to f of x is a primitive polynomial, and this is quite clear to understand, right? You can immediately do it for any rigorous polynomial, right? Because if you have this sort of a polynomial a0 plus a1x till an x to the power n, and the GCD of the coefficients is D, so you can write it as, let's say, some D times k1 plus some D times k2 x and so on, plus some D times kn x to the power n, well, each of these k1, k2 till kn are co-prime. That comes from the usual definition of a GCD, right? It's the greatest common divisor. So if I just divide by t, we'll get the coefficients to be k1, k2 till kn, and they will be co-prime. So the GCD must be 1. Fine. Right. Fine. Moreover, something immediate also you can observe, that suppose f of x is not primitive, then what do I mean? Then the GCD of the coefficients does not equal to 1. So what does that mean? That means that there exists some d greater than 1 such that d divides each coefficient. Now d is an integer, right? So d has some prime factor. What does that mean? That means that there exists some prime p such that p divides each coefficient. Okay, is it clear? So whenever you have a polynomial whose which is not primitive, you will always get hold of some prime which divides each of these coefficients, and that is something which we will be using now. And this is one of the most important theorems of this section, which is called the Gauss lemma. And what it says is that the product of two primitive polynomials is always primitive. So the product of two primitive polynomials is primitive. Okay, the product of two primitive polynomials is primitive. Let's prove it, and the proof is quite simple given the observations we have already had, given we have already done all the hard work, right? Proof. Okay, so right, so our first sort of an intuitive approach should always be by contradiction in such cases, where we do not have to estimate things, or we do not have to bring out certain outputs from the proof. If our goal is only to prove a certain statement for certain purpose, one of the most important applications or most important approaches is always contradiction, right? So let fx times gx be not primitive, where fx and gx are primitive. Okay, what does this mean? This means that there exists some prime dividing the coefficients of the polynomial fx gx, right? Now what we do, now this is the trick, let us choose a map sigma from z to zp for this p. Okay, say the prime p. Okay, then what we can do, we can talk about the extended map, right? And consider the obvious map sigma tilde from zx to zpx. What do we conclude from here? It is quite immediate, right? Then sigma tilde of fg, which is by ring homomorphism sigma tilde of f times sigma tilde of g, this should be 0, right? Because this prime divides every coefficient of this polynomial fg, and this, what does? It basically reduces each of the coefficients modulo p. So if I reduce each of the coefficients modulo p of fg, that will become 0 because p divides each of the coefficients. So this is equal to 0, right? But here comes the catch. What is the catch? Z px is an integral domain, right? Why? Because Zp is a field, so it's an integral domain. And moreover, since f is primitive, g is primitive, so the GCD is 1, so there does not exist a prime which will divide every coefficient. What does that mean? That means that sigma tilde of f is non-zero and sigma tilde of g is also non-zero, because the coefficients, all the coefficients never become 0 modulo p for any prime. So what does that imply? So that contradicts the property that Zpx is an integral domain. Clear? Therefore, what have we proven? We have proven by contradiction that the product of two primitive polynomials should also be primitive, and this is something which you need to keep in your mind for a long time. Fine. Okay. Now let's move a bit forward. Okay. Let's start via an observation first. Okay. Consider a polynomial. Let fx be a polynomial. Let's say 3 by 2x plus 1 by 3. Let's just do this polynomial 3 by 2x plus 1 by 3. Fine. You can take any polynomial, but for simplicity I am choosing this. Right. In terms of lectures, if an example is not actually very important, there's no need to talk about very complicated examples, because in lectures, until and unless we need to establish something via examples, or we want to use or explain some very important property of some example, there's no need for a very intriguing example, right? Because only thing you need to do is to visualize what's happening, or rather at least claim something in future having an intuition from this example. So can I write this as 9x plus 2 by 6, easy LCM. So I can write this as 1 upon 6 times 9x plus 2, right? So is this a polynomial in Z? It is, right? And this is a rational number. Clear? Okay. Let us take another example. Let us choose the polynomial f of x to be, let's say, 1 by 2x plus or rather not 1 by 2x, let us choose 3 by 2x plus, okay, let's choose 3 by 2x plus 6 by 3, it won't work well. Yeah, let's say 6 by 5. Okay, fine, let it be 6 by 5. Okay, now, so I can write this as, observe that I can take 3 outside, so this becomes 1 by 2x plus 2 by 5. So this becomes 3 times 5x plus 4 by 10. So this becomes 3 by 10 times 5x plus 4, right? So this, now you can observe that this is a polynomial in Z for sure, but this is a primitive polynomial as well. In the previous case it was also a primitive polynomial. In this case also it's a primitive polynomial, and this is in Q. Now can you observe that this is true for any polynomial over the rational field? Can you claim this? Because that is the only thing which we require to do, right? If I'm able to write the polynomial as with the coefficients explicitly being, suppose for example, say a0 by b0 plus a1 by b1, so on and so forth, then I can take hold of the LCM of the denominators in some sense, bring out all the numerators outside, the common factor of the numerators outside, and I can do the similar sort of a manipulation to do the same thing. Hence, consider this lemma. Every non-zero fx in Qx has a unique factorization, fx equals to Cf times f star of x, such that this C of f, this is actually a constant coming from Q, it is positive, and f star of x is in Zx, which is primitive. Is it clear? Okay, fine. Now see, proving this thing, see what I claiming is that CF is positive. So suppose if I work with only positive polynomials where all the coefficients are positive, will it cause a problem at any chance? It won't cause a problem, right? Why does it? Okay, let me claim it in general. Proof. So what we are concerned about, doing the same thing, right? Whatever we did as in the examples. So suppose I write f of x as a0 by b0 plus a1 by b1x, so on and so forth till an by bn x to the power n. So this is the polynomial from Qx. Is it clear? Let b be b0 till bn. That is the product of all these denominators. Now if I take gx to be b times f of x, then what can we see immediately? That b times f of x actually reduces all these denominators to 1. The numerators be whatever it can be. We are not, that's not a matter of concern, but after all this is in Zx, right? So one part of the proof is done, right? That is, we are able to take a polynomial from the rationals and project it into polynomial in the integers. The next thing what we want to do is that we need to find out a more reduced form where there is a rational number outside and the left polynomial is a polynomial over the integers, which is primitive as well. For that, what do I need to do? I just need to calculate the GCD of the numerators, right? And then divide by it, we are done. Exactly that, right? So, sorry, yeah. So choose D to be plus or minus D. I'm telling this, where D is the GCD of the coefficients. of gx. Okay, we could have done both of these things together here as well in fx. Just take the the common divisors of all these a0 till an's and multiply these b zeros, but rather let's do it in a more systematic way. See, what did we do in this case? In the first case, observe that first thing what we did is that we took out the common denominator outside. Just seeing at the polynomial, we took out the common denominator, then did the rest of the things, then multiplied this up, brought it outside, and we were good to go. Right? So we are doing the same thing typically. We are doing exactly the same thing, right? We are doing exactly the same thing. Fine. So what is the GCD of the coefficient? And the plus or minus sign is basically concerned about the fact that if the GCD comes out to be negative, then capital D will be positive. If D is positive, then it remains positive, because we need to talk about the coefficient CF to be positive, and we'll see that it actually comes out from here only. Okay. So what do we do is that so what should be B by D f of x? This should be, yeah, so this should be 1 by dgx, right? Is it clear? But then what happens? See, this d is the GCD of all the coefficients of gx, so this is still a polynomial over gx, right? And it's a primitive polynomial, right? And it's a primitive polynomial because we have taken all the common factors and divided the polynomial by that, so it's primitive. This is primitive, right? What is the next step? We are done, right? We are typically done. We have not yet claimed the uniqueness, but we are done. How are we done typically? Now, so how do I relate it from here, right? How do I need to write f of x? This is the way a proof is done actually. You work backwards. Okay. Now I need to write f of x as some rational number times f star of x, but this is the primitive polynomial from G, right? So can I write f star of x as, let's say, 1 by d times g of x, right? Because it's a primitive polynomial over z. Therefore my f of x becomes d by b times f star of x. Are we done? Can I choose this to be the content of f? So we are done, right? So we have an expression as we required. Just relate this proof to the way we were calculating the examples. Okay, fine. But now we also have to prove the uniqueness, right? So uniqueness. So let I'm able to write fx as some e times h of x, which is a second such factorization. Okay, a second such factorization. Fine. Okay, fine. So now observe the following. So if I claim that this is the second such factorization, so what do I have in hand? This means that my e is a rational number, is a positive rational number, right? And what more do I have? That hx is primitive. Hx is primitive. Clear? Clear? Okay. So therefore, what do I have? I have the content of f times f star of x equals to f of x equals to e times h of x. In other words, what do I have? I have f star of x as e by the content of f times h of x, right? This is what I have. Now what do we know? Now I know that this is primitive and this is primitive. Okay, let's first let e by the content of f be equal to u by v in least form. Okay, in least form, that is u and v is having GCD 1. I can do this. Then what do I have? I have v times f star of x equals to e times h of x, sorry, u times h of x, right? Now what we need to do, so u is a, what do I have? U is a rational number, v is also a rational number, right? Right? What can I claim more? Yeah, I'm doing it correct. So CF is a rational number, if E is a rational number, I'm writing this in the least form. Yeah, actually, no, right, these are integers, right? Because if I have calculated the least form, so then u and v become integers, right? Where u and v are integers, right? Right. Okay. Right? So now we compare the coefficients. We compare the coefficients on either side. What do I have from here? Now v, so v must divide u times h of x, but v doesn't divide u, so this means v divides hx. V is an integer, that means V divides every coefficient, that is the only possible case, every coefficient of hx, but hx is primitive, the only common factor of the coefficients of hx is 1, this implies V must be 1. And similarly, u must also divide the left hand side, so u must also be 1 by the same set of arguments. What do I conclude? So I conclude from here immediately that firstly f star of x must be equals to h of x, right? Moreover, this implies also right, E upon Cf is equals to U by V, which is 1, which implies E is equals to Cf. Therefore, the factorization is unique. Clear? Right. Now, this proof was actually very simple. We didn't use anything very complicated. It is just standard, sort of a standard number theoretic proof, right? All number theoretic proofs are like this, right? We use the division algorithms, we use the reducing of rationals, then we use the Euclid's lemma, so on and so forth. So it was, in some sense, it was sort of a number theoretic proof, but rather it has some very important consequences, as we'll see. For example, the first corollary is very simple to observe. Okay, that is, if f of x is a polynomial in Zx, then the content of f should be in Z. Why? A quick check. What do I have? So let me just calculate out the content, right? Nothing I need to do. If f of x in Zx, then 1 by d times f of x is primitive, where what was d? D is the GCD of coefficients, right? Working with any condition will do, because we have seen that once we attain a factorization as per the previous theorem, then the factorization needs to be unique, right? So whatever factorization we are going to conclude from here, it must be unique. So what does this imply? This implies that 1 upon d times f of x is equals to some f star x, where f star is primitive. So f of x can be written as d times f star x. But what is f star x then? What is f star x? Or rather, I need to be in accordance with the previous theorem. So a more general way of talking this is in the following way. Okay, it's getting a bit, yeah. So 1 by d times f of x is primitive. I need to be in accordance with the previous theorem, right? So I can write f of x as d times 1 by d f of x. Yeah, this will do. Yeah, this is in accordance with the previous theorem. I mean, the structure is in accordance with the previous theorem. For the first time, viewers might find a bit confusing, so I try to write as much steps as possible, right? What do I conclude from here? This is primitive, right? And so this must be the content of f, but this is obviously an integer because we are considering the GCD of all the coefficients. The coefficients are all integers, right? So this must be in C. What do I conclude? That if you have so if you have a polynomial over Z, then the content is actually an integer itself. Okay, a more general definition of content, if you have already concluded the way we have calculated the content. So in general, if R is a, let's say, UFD, for example, because we want to talk about the GCDs existing, so let's just take it for UFD. Okay, the uniqueness of GCD in terms of units, right? So if R is a UFD, then if f is in Rx, we usually define the content to be the GCD of the coefficients of f. Okay, do not get confused by the way we talk about GCDs in terms of integers, because the more general definition of a GCD was, it is the generator of the ideal, right? It is the generator of the ideal which is generated by all of these coefficients, for a more general definition. For example, if you find it more confusing, just take it to be a PID, then it will be more clear, right? Is it clear? Fine, right? Because in case of UFDs, you have a different sort of a definition. If you recall that, how would we have defined the GCD? If you recall that two elements, you take their factorization, take the respective powers, take the minimum of those powers, and then take the GCD. We have covered this in the previous lecture as far as I remember. But for in other aspect, to talk about the GCD as we are defined in terms of ideals, you can just assume R to be a PID. Then in other sense, if to talk about it in a more general way, if you consider any general definition of a GCD in any ring you like, be it a PID, be it a Euclidean domain, be it a UFD, if you get hold of the GCD of all the coefficients, then that GCD is defined to be the content of the polynomial. Okay, let me not go into any ambiguity. I guess this is clear. Fine. Okay. Another corollary, which is again very important, is the following, that if f of x is in qx is such that I can write f of x as g of x into h of x in qx, then the content of f is the content of g times the content of h, and the primitive factors of f is the product of the primitive factors of g and h. Okay, fine. So then the proof is again very simple. Why is it so? Because if I can write f of x as g of x into h of x, now g of x and h of x are also polynomials from Q, so I can write g of x as the content of g times g star of x, where g star of x is primitive. Hx can be written as the content of h times h star of x. So this implies, so we are in commutative rings. This is cg times ch times g star x times h star x, right? And since this factorization is unique, we are good to go, right? So this must be f star x due to uniqueness, and this must be the content of f due to uniqueness. I hope this is clear, right? Right. Now comes the Gauss theorem, which is actually the one we intended to do, and now I can say clearly that the Gauss theorem is very easy to prove, provided that we have already done all the hard work, right? Because in most books you will see we are going to prove the Gauss theorem now, but before, let me just give you sort of a pre-climax. In most of the books, all these things what we did before introducing the Gauss theorem would be done inside the proof of Gauss theorem. That's what makes it a 1.5 page long proof, and you feel that it's okay, so that's an utterly complicated proof. Nevertheless, what we did is that we sort of broke it down into into small bricks, and now we are going to construct the house, which is the Gauss theorem, right? I often try to give very practical examples, but I then find myself to be confusing, right? So this is the theorem of Gauss, and now it's very simple, provided all the work is already done. So if Px is a polynomial in Zx, which is not a product, so it is not a product of two polynomials in Zx, each of degree less than the degree of P, then Px is irreducible in Qx, right? Isn't that a very strong tool? So this immediately, what does it do? It immediately gives you a proof, or rather not a proof, a tool for irreducibility of polynomials over Q, right? Isn't that interesting? Right, let's prove it. Fine, okay, so let's prove it. Proof. And the proof is, as I said, very simple. If I can write fx as gx times hx in qx, what do I need to show? That the polynomial is irreducible over qx, right? So then what can I do? I can write this as the content of g times the primitive polynomial g star x. So let me write it directly in this way: content of g times content of h times g star x, which is the primitive polynomial over z, h star x, which is the primitive polynomial over h. Okay, this is in qx. Okay, now the content of g times content of h is equals to the content of f. Now f was a polynomial from where we have chosen f. Why are we working with f? We were working with p, right? Okay, so I chose the wrong notation, I'm sorry. P. Yeah, I often make this mistake. P. Now p was a polynomial over integers. So we have already proven that the content of a polynomial over integers is in integers. So this must be in integers. Right? Right? Therefore, my p of x is equals to the content of p times g star of x times h star of x. But what do I conclude from here? Now this is pretty simple to observe from here. See, c of p, this is an integer. You are multiplying it to a polynomial which is also over an integer. So this is a polynomial in zx. This is also a polynomial in zx. Right? What does it say more? Doesn't that give you a factorization over z? Right? So this is immediately is a factorization of p in z. What more can you say from here, right? What did I have in Z? P cannot be written as a product of two polynomials of lesser degree, right? So what does that conclude? That concludes that either the degree of P is same as this, that is the degree of P is same as this, or the degree of P is same as this. What does that conclude? Say it with me. What does that conclude? That concludes that it is irreducible, right? It is irreducible over Q. So we are done. Right? Because if the degree of P is equal to the degree of this polynomial, then this must be a constant polynomial, because we are working over integral domain. So if this is not a polynomial of degree 0, then the polynomial will increase more than P. It's not possible. So one of them must be a constant polynomial. That means one of them must be an element from Q. Q is a field, so that element must be obviously a non-zero element. Then that element must be a unit. So it's irreducible. Got it? Fine. Very clear to see these things. So what we have proved is that, if I have a polynomial which does not split into two polynomials of lesser degree over Z, then it is irreducible over Q. Okay. Now see one thing. Now one very important remark, and this is also given to be an utterly complicated proof in most of the books. What is that? That observe that if I choose, let us choose that Z be a UFD, Z be replaced by some UFD R, and let Q be replaced by the fraction field of R. No problem in that. The proof in any case doesn't require any specific conditions over integers or any specific conditions over Q in any of the things we did previously, right? Because we had already, just the things which we had used were divisions, right? Divisions over the lower ring or divisions over the upper ring. In any case, mostly divisions over the lower ring, and we know that over UFDs divisions over the lower rings exist, right? So we can replace in all the above proofs by Z by an UFD, any UFD R, and Q by a field which is the fraction field of R. What does that prove? Doesn't that prove that, so it proves actually that if R is a UFD, then Rx is a UFD, isn't that right? Isn't that the thing? And we know that fields are UFDs, right? So it proves in general that if F is a field, then Fx is a UFD. Furthermore, what does it prove? It proves that f of x1 till xn polynomials over field of n variables, which you can actually write as xn minus 1 of xn. Okay. Now see, you can prove that this is a UFD by induction, right? Right. So this is a UFD. Assume by induction this is a UFD. So this becomes of the form Rx. So this is a UFD. So it proceeds by induction. Therefore, polynomials over fields of n variables is also an UFD. Is it clear for everyone? Now what we do is prove one of the other most important theorems regarding the irreducibility of polynomials, and that is called the Eisenstein's theorem. Eisenstein's theorem. So what does the Eisenstein's theorem say? It says that let f of x equals to a0 plus a1x till an x to the power n, and it belongs to zx. Okay. If there exists a prime p dividing ai for all I less than n, p does not divide an, and p square does not divide a0, then f of x is irreducible in qx. Okay, let's see the proof. Okay, have you got what I'm trying to prove? I'm trying to prove that I'm giving a polynomial in zx. P does not divide a0. P divides a0, P divides a1 till P divides an minus 1. P does not divide an, and P square does not divide a0. Then this polynomial must be irreducible over qx. Okay, proof. Now first thing first, observe that if f of x is not equal to g of x times h of x, such that the degree of g is less than f, the degree of h is less than the degree of f, degree of h is less than the degree of f, then fx is irreducible over q directly, right, by Gauss lemma. by Gauss lemma, right? So therefore, let f of x equals to g of x times h of x, which is equals to say b naught plus b1x till bm x to the power m times, let's say, c naught plus c1x plus ck x to the power k in zx. Okay, now what do I have now? So a0 must be b0 times c0 and an must be bm times ck. Okay, now what do I have? Now p divides a0, that implies that p divides b0 or p divides c0 by the Euclid's lemma. Also, what do I have? P square does not divide a0, that means that, what does that mean? That means that p square does not divide b0 and p square does not divide c0. No, I can't say about this, sorry. P square is not a prime, I'm extremely sorry. I wanted to say that this is equals to b0 times c0, I'm extremely sorry. I wanted to mean this, right? That is, what I actually wanted to write is that p square does not divide b0 c0, right? But p divides one of them, p square does not divide their product. Now if p would have divided both b0 and c0, then p square would have divided b0 times c0. That's quite an easy observation. What does these two mean? So these two concludes that, therefore, okay, let me not write it in such an ill-mannered way. Therefore, p divides only one of them. That is what I meant, only one of them, right? So without loss of generality, let p divide c0. Okay, and specifically p does not divide b0. Clear? Okay. Now what more we have? What more we have is that an is equals to bmck. I guess we have already written it, but still, rather than, not a problem. And we have p does not divide an, right? What does that mean? That means that p does not divide bm and p does not divide ck. Fine. This is something which we want to use because we are working with C, because without loss of generality I have claimed here that p divides c0. Let me use this. And that is exactly the tool what we are going to do. Now, so let C, so there are only a finite number of coefficients, right? So I can make use of such an argument that let CR be the first coefficient of hx, these were the coefficients of hx, right? Which is not divisible by p. Which is not divisible by p. That is C0, C1 till CR minus 1 are divisible by p. Are divisible by p. Okay. Now observe that now if r is less than n, okay, then p divides ar, and observe that b0 times cr can be written as ar minus b1 cr minus 1, so on and so forth till br c0. Where does it follow? The Cauchy product, simply from the Cauchy product, right? Is it clear? What does this mean? Observe very carefully what does this mean. Now p divides each of these CRs, right? CR minus 1 is divisible by p, CR minus 2 is divisible by p, so C0 is also divisible, C0 is also divisible by p. And what do I have in terms of the hypothesis of f? That p divides every coefficient except a. R is less than n, so p must divide ar as well. Therefore p divides the RHS. That means p divides b0 CR. But that means by Euclid's lemma again, p divides b0 or p divides CR. But we have already started with the hypothesis that p does not divide CR. That should mean p divides b0. But then this is a contradiction. Contradiction to what? Contradiction to the fact that we had assumed that r is less than n. Contradiction to r is less than n. Therefore, what do I need to have? Therefore, r must be equals to n. But if r is equals to n, what does that imply? K is equals to 0. What does that imply? Hx is constant. Okay, if in some sense I have mixed up the coefficients, please pardon me. Just list that if I might have mixed up the polynomials. So what was k? Which was k? Let me go back. Where did I start the proof? Yeah, so k is 0, right? R is equal to n, k is 0, right? Yeah, so we were working with this polynomial, right? right? Yeah, I got confused myself. I'm sorry, but I got confused myself. Yeah, so right. Yeah, so if r is equals to oh wait. Sorry. If r is equals to n, then what do I conclude? So then m must be 0, right. So the polynomials in B, right. So what do I mean basically is that the polynomial h would be exactly the polynomial f. That is what I meant. Right. That implies m is equals to 0, and so I chose that to be just gx is a constant, non-zero constant obviously, hence a unit in q or qx. Well, what does it mean? It means that f is irreducible. Right. I got confused a bit as well because I wrote the notations far above, and then while proving I went below. Fine. Now it's clear, right? Okay, fine. Now there's a very important polynomial which is often in use, and it's more prevalent when we talk about field theory. The next course will in continuation with this will be field theory, and this course will be named as rings and fields, as you would have already seen. So there we will be explicitly talking about this once more, but let's talk about it here. Definition: if P is a prime, then the pth cyclotomic polynomial is phi px, defined as x to the power p minus 1 plus x to the power p minus 2, so on and so forth, plus x plus 1, which can be written as x to the power p minus 1 by x minus 1 for x not equal to 1. Okay, clear? So now we have a very fine observation, or you can also take it to be a corollary of the Eisenstein's theorem, that is phi px is irreducible over qx. Let's see. And the proof is exactly very simple, just a little trick is required. Observe that f of x is irreducible if and only if f of x plus c is so, where c is some constant, right? Now observe now phi p of x, which can be written as x to the power p minus 1 by x minus 1. So I chose it to be x not equal to 1, but I actually don't require it because x is an identifier, it's a variable, right? So phi px, x to the power p minus 1 by x minus 1 is irreducible if and only if phi p of x plus 1, which is x plus 1 to the power p minus 1 by x, is irreducible. Now observe that this is actually can be written in a very simple way, right? Because observe that this can be written as, now x plus 1 to the power p minus 1 is equals to x to the power p plus some elements, all of which will have coefficients a multiple of p, right? Because we will have the binomial coefficients in terms of p. This is a simple binomial expansion which is prevalent because we are working in commutative rings. Plus we have 1 here minus 1. So this is x to the power p plus things. Lastly here we would have p, choose p minus 1, right? So yeah, am I doing, yeah, correct, right? This is what we will have, right? So fine, yeah, right. So therefore x plus 1 to the power p minus 1 by x would be x to the power p minus 1, so on and so forth till, so p choose p minus 1 is just p. So what do I conclude from here? Now all of these elements will be divisible by p, right? Therefore p divides every coefficient, because all of these are binomial coefficients in terms of p. Those are of the form p choose r for r is less than p minus 1 greater than 0, right? And p divides, so this is my a0, and p divides a0. P squared does not divide a0 clearly, and it's a monic polynomial, so p does not divide 1 as well. Therefore by the Eisenstein's criteria, phi p of x plus 1 is irreducible over q, which implies that phi p of x is irreducible over q. Is it clear? The use of this we will see when we will be getting indulged into the study of field theory. There we will be requiring it in a lot, but take it as an example for now. Another important application of the Eisenstein's theorem is that if let's say a is an integer such that a is not a perfect square, A is not a perfect square, that is I cannot write A as B square for some B. Okay, then x to the power n minus A is irreducible over Q for n greater than or equal to 2. And the proof is again very simple. Proof, what can we do? Since A is not equal to plus or minus 1, there exists some P which divides A, but P square does not divide A, as A is not a perfect square. Right? Therefore, apply the Eisenstein's criteria using this P, and we are done. Right? So this actually claims that there exists arbitrary polynomials, irreducible polynomials of arbitrary degree n over Q. Nevertheless, fine. So we end this lecture here, and from the next lecture we will be trying and indulging into the notions of field theory. We are not gonna do Galois theory here. I might try and bring up some other lecture series on Galois theory specifically, but our main concern will be field theory, where we will be talking about algebraic extensions, algebraic numbers or elements, then finite fields once more in very brief. We will just brush over finite fields, and assuming that you guys have already seen the lecture on finite fields in this course, then we will talk about splitting fields, something which we have also introduced already in this course, normal and separable extensions. These will be very important. And here we will be making use of this cyclotomic polynomial. And one more thing I will try and introduce in the field theory course, which is not in general done in the other courses, is the notion of constructible numbers. Okay, and in between them there also be the notion of the finite extensions or finitely generated extensions, so on and so forth. But these will be the topics which will be of main concern. Clear? And already Jyotishko would have already introduced you to his course on group theory, and I think you guys have already seen that course, and I believe that that's an extraordinarily beautiful course on group theory, right? Fine. So let's move on to fields.